orientation is by Victor Albert. I give you the word, Victor. Go ahead. You have 55 minutes.
Thanks. Thank you for this very unique opportunity. I really wanted to be there in person, but unfortunately I can't make it. Thank you for pointing to the audience. Hi, everybody. I would there you go. I would very much hope that we can have more of a discussion, because it's very hard to gauge how much people are understanding if there's no participation or reflex on the audience. So I'm going to talk to you today. Well, let me fix the animations here. Sorry about that. I'm going to talk to you today about something that I noticed, namely a lack of a duality or an underdeveloped duality in molecular state spaces that really should have been developed 100 years ago. So quantum mechanics, when we upgrade things to the quantum world, one of the core principles or core tenets of quantum mechanics is conjugacy, or duality between different degrees of freedom. So this is manifest in Heisenberg's uncertainty relation, non-commutativity of observables, and things like that. And the most famous one is, of course, the uncertainty relation between position and momentum, or the conjugacy between his position and momentum of a harmonic oscillator. So there, the position state of a harmonic oscillator is labeled by a real variable. So you can think of that space as representing a particle on a line. And the momentum states, exists a set of dual states that are these momentum states that are, instead of being very localized in position like the position state, these momentum states are the eigenstates of the momentum operator, and they're very delocalized in position space. And there's a Fourier transform between them. So I think everybody's familiar with that. But this kind of Fourier duality runs much deeper in other spaces. So the state space of a qubit has this as well. And there you can think of the two computational basis states of the qubits as 0 and 1 as being the states of a particle on a discrete sort of pair of states. And those are eigenstates of the Pauli-Z operator, and the eigenstates of the Pauli-X operator can be thought of as these dual momentum states of a qubit. And in the same sense as in the harmonic oscillator, there is a Fourier-like transform that goes in between them. And you're familiar with that. What is that gate that converts between these two bases? Anybody? I'm guessing if somebody screams out, I can't hear them, right? We can test it. Let me know what this, what?
State or gate or what?
What gate is it? What gate goes between 0, 1 and plus minus bases on a qubit?
Hadamard, no?
Hadamard, that's right. So that's the discrete analog of the Fourier transform for the qubit. So this is all fine and good. These are super well-established relations. Why am I talking about this? Well, to name another more maybe exotic example is the duality that happens in condensed matter physics, where you look at electron wave functions. And there, depending on what you want to do, you pick kind of two different bases as well, among others, that are sort of dual to each other. So if you're dealing in a solid state, you deal with like these periodic wave functions, and the electrons are spread around. So you deal with block functions. But if, on the other hand, you're dealing with more localized electronic states, like those in a molecule, electronic states in a molecule, then you deal with Wannier, these things called Wannier functions. So this position momentum duality is very much underpinning the topological classification, or like condensed matter systems and their topological classification. In case you're familiar with it, I guess I'll just say that this duality is actually important in that classification. And along those lines, we wanted to think about defining or establishing a duality between the position and momentum states of a molecule. And the motivation for this initially was error correcting codes, trying to encode a qubit or logical information in a molecule. But I think this kind of goes a little bit deeper than that, because the applications of dualities really aren't limited to error correction per se. They're also relevant to quantum communication, quantum cryptography, and quantum simulation, and quantum algorithms as well. So any kind of quantum system that you want to study and apply and use for applications nowadays basically has to have a notion of duality for it. And when I was coming at this from the angle of error correction, I actually found something very surprising, that this duality had not been formulated. Namely, the position states of the molecule had not even been defined for general molecular state spaces. So something that I thought would have been done was not done. What had been done was the momentum state space of molecules. And below this slide, I list a whole bunch of people who did this, starting with the late 1930s. So over the past 100 years, there has been a program basically classifying the momentum states of a molecule with such and such a symmetry and such nuclei in its kind of rigid configuration. So when I say momentum state, I guess I should preface that with angular momentum state. So as opposed to the linear position momentum of a harmonic oscillator, now we're going to deal with angular variables. So momentum states of angular momentum, and position states would be of angular position or orientation. So the point of this, the point of this paper was to develop a theory, a duality between position and momentum states of molecules, which first involves writing down the position states and then determining what the Fourier transform is between them. So that's kind of the overarching message. And I'm going to have some slides about this, and then maybe the next time, depending on how much I get through, I can also do some examples. So does this, if this doesn't make sense, feel free to interrupt and ask me about anything at this point. Okay. So there's a couple of clarifying points I want to make before we get into sort of the defining position states. And that is, the first point is about symmetry. So symmetry is a kind of an interesting thing. So would you say that an airplane has a symmetry? Kind of, right? Because, the wings looks the same. And if you reflect it through if you somehow were magically able to reflect it through the plane, then you could imagine kind of it looking the same. Your face, is almost symmetric as well. But, the key word here is almost. The issue here is, while these types of objects look quite symmetric to us, there is no their configurations, their possible states are not restricted due to this symmetry. So we don't need to take into account their symmetry in defining all of their allowed configurations. Why not? Well, because the airplane, the molecules, the atoms making up the airplane, there's so many of them that when you say, if you were able to magically swap, reflect the airplane through its plane that bisects it, there would be no need to account for spin statistics, because there's just so many atoms, and not every atom will snap into the position of the other atom of its partner. So the types of symmetries we talk about, when we talk about microscopic objects, are really, do not determine the different configurations of the object. Moreover, for the airplane, we can't even do kind of this reflection through the plane. Similarly, for a molecule that I drew here, this is I forget what this is, but it's got a methane group here. Anyway, similarly for this molecule, it has 3 identical hydrogen atoms. And when you have identical atoms, then you have to start to worry about whether any operations that will permute those atoms will then leave the rest of the molecule alone, and therefore be a symmetry of the molecule. If that's the case, then you have to worry about Pauli spin statistics arising. So because the atoms are identical and they're either bosons or fermions, the nuclei are either bosons or fermions, they have to satisfy spin statistics. Give you either plus or minus 1, depending on how many permutations happen. However, with this molecule, when you rotate it like this, you are permuting the 3 hydrogen atoms at the top, but the bottom guy is moving to a different position. And so these 2 orientations are distinct, and they're not identified by a symmetry, because this operation that rotates this molecule does not rotate it back to the same configuration that it started with. So this is an asymmetric molecule by this notion. On the other hand, when you now have a molecule which has some handful of atoms, and there is an operation that exchanges identical spinful nuclei and maps the molecule back to itself, this is a symmetry. And this is what I'm drawing here with hydrogen molecule, H2. The arrows here are representing the nuclei. And when you take this molecule and you rotate it around like this, then because the nuclei are indistinguishable, you are back to the same configuration of the molecule that you started with. Namely, the final configuration is identified with the initial one because the atoms are indistinguishable. And so you have to take into account the action of the symmetry and perform some kind of identification of all symmetric configurations in order to get the full space of available orientations of this molecule. Okay. So this is a long-winded way of basically saying that you have to do something when there are identical spinful nuclei and when there are symmetries that permute them. So this is another clarification slide, in case anybody's familiar with this classification from chemistry into symmetric tops, asymmetric tops, and spherical tops. Can anybody raise their hand to see if they're familiar with this? Okay, all right. So maybe this is for those people, but there has been lots of classifications of, in chemistry, and I want to clarify that the one I just mentioned is a classification of molecular Hamiltonians. What we're doing is something that takes a step back from that. It's doing the classification of molecular configurations. So once you have a state space or a configuration space of all the possible states of position or momentum, then on top of that, you can add a Hamiltonian. In fact, you can add any Hamiltonian that respects the symmetries that are used to define the orientations. And those Hamiltonians are classified into these kinds of tops. But the classification into tops of the Hamiltonians is not directly related, or is not directly guiding the classification into different configurations. So, for example, what are called asymmetric tops, so even though this is a classification of Hamiltonians, people often call them the molecules that the Hamiltonians are describing as the names of these tops. So, for example, water is an asymmetric top, but water has a symmetry because you can rotate around the z-axis and permute the 2 hydrogens and have the molecule be invariant under that. So it's an asymmetric top with a symmetry. Similarly, the molecules that are symmetric under the 3 exceptional subgroups of SO3, which is tetrahedral, octahedral, and icosahedral group, they're all called spherical tops. So this is too coarse-grained of a classification. But those molecules are clearly very different with very different symmetries. So we're providing a basis of orientations of position states. We're not diagonalizing any Hamiltonians, as is very common in chemistry. We're just providing a very conceptual basis and notion of duality for the state space that underlines positions and momentum. I mentioned, I hoped to be somewhat surprising you when I say that these states have not been developed before, because to me it seems like a very canonical thing that one would want to think about. However, there are reasons that I became convinced this has not been developed before. Namely, because chemical experiments most of the time consider molecules in the gas phase, where they're vibrating and jiggling and spinning around, and where the dominant states that the molecules can have are states of fixed angular momentum. And so in angular position states were not really relevant to experiment. So they didn't bother to do them. There was one exception that this slide covers to that story. And that happened in the early 90s, where people started to be able to orient molecules using strong electric fields. And if you do that, then right after the field has shined on the molecule will snap to a particular orientation. And that stabilizes a position state for the moment. And there was a set of theorists looking at understanding these position states, and they called them pendular states. I don't know if anybody's heard of that. But these pendular states are basically the same types of position states we'll introduce. However, they are defined to only kind of jiggle around a particular axis that is determined by the electric field that is shined on the molecule. So in some sense, these pendular states are local, subsets of this whole entire big configuration space of orientations. And that's what we're going to be talking about today. Because if you upgrade from local to global, you'll see that there's actually a lot of interesting topology that these spaces have. And you would not be able to see that if you only studied perturbative expansions around a fixed orientation. Okay, so this, I hope, sets the background a little bit. Still welcome any questions.
Victor, there's no possibility for questions. It's only me that has a microphone. The audience does not have a microphone because there will be feedback. So that's why no questions.
I see. Well, then I guess if you want to ask any questions at any point, I'm happy to hear them. The microphone has a wire attached to it, or I guess you say if you take it back there, then there'll be feedback.
No, but it will take some time, so...
Okay. Okay, so to start this classification of orientations, we'll start with something very simple, and that's we're going to restrict to 2 dimensions. So we're not going to look at 3D orientations because there the group of rotations is SO3, special orthogonal group, in 3D. The group of rotations, and that group is not abelian. If you restrict to 2D, if you pin down your molecule to only rotate on a table, then the possible rotations that it can implement form the group SO2, and that group is abelian, and it's very simple. So how do you figure out the different orientations of a molecule sitting on a table? Well, so let's take this diatomic molecule to begin with. It's the same as a pencil in terms of its class, I guess. And what you do is you take a reference orientation of this molecule and you apply a rotation to it. When you do that, you rotate it over here, fine, by some angle phi. If you go back to the reference orientation, you rotate by a different rotation, phi prime, not equal to phi, you go to a different orientation. And you do this for all the different rotations, and you get a different orientation every time. And this means that the space, the configuration space of orientations of this molecule or pencil is the same as it can be one-to-one identified with elements of the group SO2, with namely angles phi from 0 to 2 pi. And any function or wave function, which is the same as a quantum state, can be expanded in a basis of either position states on this molecule, which are the orientations labeled by phi, or the momentum states, which are labeled by integers j. So phi, as I already explained, is the orientation. J is an integer because it's describing how the molecule is spinning, whether it's spinning clockwise or counterclockwise, and with how much angular momentum. This is quantum mechanics, so the angular momentum is quantized, and so it's quantized in units of some integer, and then the sign of it tells you the direction the molecule rotates. And you probably are all familiar with this. The position and the momentum basis are dual to each other in this way. So the positions can be expanded to the momenta and the positions, because both are bases. And there's a Fourier transform, which is called the Fourier series, that goes between them. So the j-kets are, when you use the j-kets, you're effectively doing a Fourier series of a function. But physically, you're expanding a wave function in the momentum basis of the planar rotor. Okay, so this is the most simplest example I have. And we're going to kind of do a classification of all the other types of planar rotors that you can have that now will have some symmetries to them. So this is the one that we have. This is an asymmetric rotor, because every orientation is in correspondence with a different rotation. So there's no rotations that leave the thing invariant. On the other hand, there is, if you look at a dumbbell or disulfur molecule, which has no nuclei, you see there's no arrows in the balls. This molecule is the same as a dumbbell in terms of its orientations. If you think of the dumbbell as a symmetric object. And now, when you look at this dumbbell, let's pretend this end is the same as that end. When you rotate it like by pi, it will be the same, because these two ends of it are indistinguishable. So in the case of the disulfur molecule, the ends are the two atoms are indistinguishable. And so a pi rotation now becomes a symmetry of this. So in the end, the answer is that this will also be a circle, but it'll be a different type of circle, because now the circle will go from 0 to pi. And when we add spin, you're going to see a different type of rotor, which is also a circle. But now, because of nuclear spin, this will be a special circle that basically has twisted or antiperiodic boundary conditions. Namely, when you take this thing called orthohydrogen, which I'll explain in the next few slides, and you rotate it by its symmetry, namely by pi, it actually will spit out a minus sign. Sorry, when you take this object, and when you look at it upside down, so when you do a passive transformation on the molecule, namely the frame that you're watching from, changes. So when you look at it upside down, it will actually give you the same state of the molecule as before, but up to a minus sign. So these are the three types of circles that basically all types of diatomic molecules can make. And they're echoing the more general classification that we have of 3D rigid bodies into these three kind of classes. Asymmetric class, where you just have an orbit of the full group. Symmetric but classical, or rotationally symmetric class, where you can identify them with classical objects, and where the only point is just to take care of symmetries without any special boundary conditions or anything like that. And then what I call pair rotationally symmetric class, which is the third one, where nuclei come into play and interplay with the symmetry, such that now the rotational state space is represented differently, using the same configuration space, but now with different boundary conditions. This already happens in 2D, which is quite interesting in and of itself. But the key point here is that in 3D, this is also more or less the same kind of story. Okay, so let's look at the symmetric dumbbell case once more, or more in detail. So in the corner here, I have the asymmetric guy, and we're going to use the states of the asymmetric rigid body to define the states that are allowed to be occupied by the symmetric body. Because of the symmetries, their state space has to be constrained. That's what symmetry does. And we're going to determine those constraints in terms of the original unconstrained state space of the asymmetric guy. What is the constraint? Well, the symmetry here is a rotation by pi. This rotation by pi I'm representing as this x operator, and it's generated by the angular momentum j, which is just that integer valued operator, diagonal in the angular momentum basis, and it's a rotation by pi, so there's a pi here. So it's -1 to the j. When you apply this operator to any admissible function of the molecule, which is going to be a function of the positions of the two nuclei, phi1 and phi2, what it's going to do is it's going to exchange the positions of the nuclei, and it's going to spit out, if you then re-identify it with the original positions, that's going to spit out a minus sign. So in more detail, this rotation moves the position of the nuclei from one to the other, and then when you exchange them back to identify that with the original wave function, because this is a symmetric molecule, you have to get a plus sign. You have to get a plus sign because there's the nuclei are indistinguishable and they don't have any nuclear spin. In chemistry, they like to call this a spin zero bosonic nuclei, but I think that's not necessary because this is basically a classical object. If you assume the classical object has indistinguishable ends. So when you constrain this, if you look at the momentum basis and you look at how this operator acts, you see that to get the plus sign, you have to constrain the momentum basis to only be even angular momentum, because the rotation is -1 to the j. Now, what about position? Well, in the case of the asymmetric rigid body, the position states were just linear combinations in this Fourier transform way of the angular momentum states. And if we just naively do that again, on this side here, on the right-hand side, if we superpose the available j that we have, the even j, in this way and giving it a phase, we actually get the position states of this molecule. This molecule also has position states. They're here. They should be labeled by pi, from 0 to pi. And what are they? Well, it turns out that these are the position states. Now, if we take these position states and we express them in terms of the position states of the original asymmetric molecule, then they will be the position state at phi. So at each position state of the symmetric guy at phi will be the asymmetric position at phi plus the position, its antipode, plus its shift by pi. And it'll be an equal linear combination with a plus sign. Okay? And the symmetry is manifest here because if you rotate everything by pi, then phi will go plus pi, this phi will go plus pi, so you go back to the same superposition of phi and phi plus pi if you apply the symmetry. So the configuration space is matched here. This is the right configuration space. It's from 0 to pi. Okay? So far, so good.
Question.
Yeah.
Questions, anybody?
Cool.
Okay, we continue.
Yeah, feel free to come up if you want to ask a question. I don't know, somebody maybe was coming up, but good. So now we get a little harder. So now we're going to add nuclear spin to the story. So now the state space that we have to deal with is not only the state space of orientations, so this circle space that I told you about, which is the space of functions on SO2, which is L2 of SO2, but now we have spinful nuclei. And here, in the case of hydrogen, we have two spinful nuclei, and each one is a spin 1/2. So this is where these two C2 objects come into play. So the full space here is this now. We have a composite space of orientations and nuclei. And this is really kind of a problem that you maybe see in your qualifying exams. This is this ortho pair hydrogen story. But I'm going to tell it from the point of view of position states as well, because those are not something that people people typically tell this story as. So you have this full space, but you know there's a symmetry, and you have to constrain it. So we play this game again. What is the symmetry? Well, the symmetry now acts in a composite way on this rotational sector and on the nuclear parts. What the symmetry does is it exchanges both the positions and the spins of the molecule. So if you look at it mathematically, it's going to be our -1 to the j on the rotational state space, and then it's going to act as a swap on the two nuclear spin factors on the two qubits of the nuclei. And so kind of in old school notation, this is how you would represent it. And then when you go back and identify this symmetric configuration with the original one, you get a minus sign because the nuclei spin half, and so they're fermionic, so they have to satisfy Fermi spin statistics. If this was not hydrogen, but say deuterium, then it would be spin 1, and this would be a plus. It doesn't matter what the sign is. What matters is that it has to satisfy a specific relationship. It cannot be, anything. In this case, it's either plus or minus, depending on which isotope you're using. So, okay, so we'll stick with hydrogen, so it'll be a minus sign. So now we have to get this minus sign from somewhere. And where do we get it from? Well, there's two ways to get the minus sign. We kind of have two factors. One is the rotational, one is the nuclear. And the minus sign could come either from the rotational or from the nuclear side. If it comes from the nuclear side, this is called parahydrogen. So who's heard of this orthoparahydrogen story? Interesting. You guys have heard of TOPS, but you haven't heard of orthoparahydrogen. So the orthohydrogen and parahydrogen are basically that give you the two ways to get this minus sign that gives you the configuration space. And so this allowable state space splits into two species or nuclear isomers, and that's what they're called. So in one case, in the para case, the minus comes from the singlet. Sorry, the minus sign comes from the nuclear state. And so the two spins that are representing the hydrogens have to be in a singlet state because that's the only antisymmetric state in this C2 cross C2 space. So the singlet state is up, down, minus, down, up. And so when you act with this swap operator, that gives you a minus sign, and you need globally you need a minus sign, and therefore the rotations have to give you a plus sign. So this again forces us, if we remember our rotational momentum states, to have even angular momentum. And this, to me, is basically this parahydrogen is basically a dumbbell because it's the same state space of as that of a dumbbell, namely even angular momentum, but just with a dangling singlet nuclear state. So in a sense, parahydrogen is basically equivalent to a classical object if you kind of remove the dangling spin state, or a classical object with a dangling spin state. It's not really occupying a different state space because it's basically the same as that of a dumbbell. But now there's a second way. So the spin statistics now induces two ways, right, to get this minus sign. The minus sign can come now from the momentum. And now, because of this availability, the momentum now has to be odd. The nuclei will now be in this triplet because they have to be even. But forget the nuclei, think about the momentum. Now it's odd. And now this is not something that you can possibly occupy by any kind of symmetric rigid body. So you had a microscopic dumbbell with identical nuclei. You cannot, with identical spinless nuclei, spin 0, you cannot occupy, it cannot have angular momentum that is odd. But hydrogen, because of this interplay of spin statistics and symmetry, can. So that's the momentum story. And this has been known for like 100 years. But now this also, so the momentum state spaces are different of these two species. One is even, one is odd, clearly. So there must be different position states. So what are the position states of this new ortho species? Remember, the momentum state, the position states of the disulfur molecule were positive superpositions of phi and phi plus pi from the previous slide, right? What do you think the position states of this odd momentum species will be? Oh, wait. Let's see. Okay, I'll just show you. But I think I can try to figure out how to get you guys to vote different ways depending on raising your hands. Will they be the same as the para species? Will the ortho species position states be the same? Anybody brave enough to raise their hand? Do you think they'll be the same or do you think they'll be different? Who thinks they'll be different? Got one. Right. Good. So the momentum states will be different. What will be the difference? Well, it turns out if you do the superposition, again, the same way as before, and then you express the result in terms of the original position states of the asymmetric rigid body, the resulting position states will be superpositions of phi and phi plus pi, but now with a minus sign. And this minus sign is important. And you'll see now why. So this minus sign is responsible basically for interplaying with the nuclei correctly to give you the correct global spin statistics when you do an active molecule rotation, when you take the molecule and you physically move it. But now, if you instead just look at the molecule yourself upside down, so now you do a passive transformation to the molecule, the behavior will be different. Passive transformations do not exchange nuclei. Passive transformations only act on the rotational factor alone. Okay, this took me like 3 months to internalize. So it's, if it seems confusing, it's okay. It was confusing for me for a long time. Passive transformations do not exchange nuclear spins. You look at the thing upside down by pi, so you rotate yourself by pi. The molecule will still be in a symmetric configuration, but the effective rotation that you've applied on the molecule in this passive way will only act on the rotational factor, okay? Not on the spin. So there won't be a swap. And because there's no swap to compensate this -1 to the j, the fact that the two species have even or odd j respectively will spit out a species-dependent sign that gives you, that can be interpreted as a topological Berry phase if I think of this passive transformation as, a slow adiabatic movement in the parameter space of the molecule. And that's really kind of one of the big take-home messages. So how does this work? Well, so if we apply this -1 to the j to the position states of the para species, it's just going to shift them both by pi, but the superposition is positive, so it's just going to spit out a plus sign. And if we take the ortho species, it's just going to shift them both by pi, but now there's a relative minus sign. So when you go back to the same state, it spits out a minus sign. And these plus and minus signs can be identified with something that's called an induced representation. So you can think of an induced representation as adding a little fiber, pseudo-spin degree of freedom to each orientation of the molecule. In the case of the para species, well, and the ortho, both the para and the ortho, the little pseudo-spin is one-dimensional. So it's just a scalar. But it transforms differently depending on the species. And how it transforms is basically defined by an irreducible representation of the symmetry group. So the symmetry group here of this dumbbell is just C2 or Z2 for the physicists. It's just do nothing or rotate by pi, right? So that symmetry group can be represented. It's abelian, meaning the operations commute. So it can be represented by just scalars. It can be represented in two different ways, such that the group multiplication holds. One is just by the numbers 1 and -1. The identity operation is 1. The flip is -1. And another way is just the trivial way, where both operations are 1. Those are called the sign irrep and the trivial irrep of this group. There are no other irreps. Then the point here of this induced representation is that each orientation of these two species carries with it a little fiber, little pseudo-spin, that transforms according to some irrep of the symmetry group. And you can back those transformations out by applying symmetry transformations to the molecule. When you apply these passive symmetry transformations, you obtain a state that should be identified with the initial state, and it will be, but up to a sign that's defined by which irrep the fiber is transforming under. In the para species, the fiber is trivial, so doing nothing spits out plus. Doing a passive pi rotation also spits out plus. However, in the ortho, doing nothing spits out plus, but then doing a passive pi rotation spits out a minus sign. So that ortho species transforms, the fiber transforms as under the sign irrep, which chemists call B of the symmetry group. Okay, so there's a group theoretic understanding here. Every orientation carries with it a little fiber, and group theory tells you how the fiber transforms when you do symmetries. And that's what's basically underpinning this classification that we were doing. Okay, and it's already manifest on the level of ortho and parahydrogen, which, at least in the momentum, for the momentum side of the story, is in undergrad chemistry textbooks. Okay, so that's kind of a little bit of the group theory. Now, to unpack what I mentioned about the topological Berry phase, let me now kind of tell you the same story from the point of view of the parameter space. So the configuration space you can think of, it's a circle, and you can think of kind of moving the molecule around on this parameter space. You can think of it as a parameter space, and so you can kind of define closed paths in parameter space. Symmetries are closed paths in parameter space. And then you can think of now the resulting operation that happens after you apply a symmetry as a Berry phase. So in the case of no rigid body symmetry, when you go, there's no symmetry, so if you come around full circle, you don't get anything, because every state is associated with a distinct rotation. In the case of a dumbbell or parahydrogen or disulfur, there is a symmetry. It's a rotation by pi. And so this circle now becomes smaller. It goes from 0 to pi. But now when you go from 0 to pi, you still don't get anything. You get a plus sign, as you saw exactly, because the momentum states are even, or you can alternatively derive this by looking at the position states. They're just interchanged, but the sign is positive. So nothing happens. However, when you take a para-rotationally symmetric molecule, such as this ortho species of hydrogen, and you do a passive transformation adiabatically, you can think of that as moving around in the circle. And now the phase that you get, there will be something non-trivial that you get, and you'll get a minus sign. And this minus sign doesn't matter how you moved around the circle. So for one, it's a Berry phase, okay? But it's a very special type of Berry phase, okay? The usual Berry phase you think about is the Berry phase of a Bloch sphere. But that thing depends on something. What does that depend on? Somebody's nodding. What are we depending on? So the Bloch sphere Berry phase depends on something, right? Anybody remember? The area, right? The area enclosed by the path. Okay, and so if the path is jiggling, then the area will be different, and the overall Berry phase will very much be geometrically dependent on the area. It'll fluctuate. However, when you have a parameter space that's not simply connected, you can have a different type of phase that only depends on the type of loop made in the space and not on any kind of geometric feature such as the area or what fluctuations in the path. That's called a topological Berry phase, or more generally, a monodromy. The sphere is a simply connected space. So in the sphere, all loops can be contracted to a point. So you cannot have a topological Berry phase in the sphere. But a circle is not a simply connected space. I can draw a loop that I can't contract because the circle has a hole in it. So that's not a simply connected space, which means it's possible to have a topological Berry phase on this space. Think Aharonov Bohm. Okay? So I say it's possible, but it's not always going to happen. There are circles, such as the first two circles that I had, that do not have a Berry phase. But the third circle that I identified, with this ortho hydrogen species, does have a Berry phase. So it's a different type of circle, different types of position states, different types of momentum states. Okay? And this one does have a topological Berry phase under passive transformation. So that's kind of like basically the story for these diatomic two-dimensional molecules. So, I do want to hear any kind of feedback from anybody to see if, there's anything I want to clear up, if possible.
Any questions? Okay, so I have a question. So you get these topological phases, no?
Yes.
And they're related to non-trivial homotopy group,
Yes.
fundamental group of your base space. So you are going to do this essentially in the end for SO3 in homologically
Yes.
So you're going to take it to SO3 and you will have there a lot of non-contractible curves and associated monodromies.
Yes, and I enjoyed reading your papers, learning about them. Yes, I'm going to take it. The whole result is taking it to SO3. That's right. That's right. But
so
yeah.
how is this related to, say, work by Littlejohn and who have studied also these configuration spaces of classical objects?
Yeah, good. Yeah. I was also wondering that, and late last year, I actually spoke to Littlejohn and tried to dig up all these classical mechanic literature. And it turns out so their work mostly centered on kind of assuming that symmetry was a measure zero set and classifying a more general, like what was it they were doing? I have notes on this, but it was like now 4 months ago. The classifying Hamiltonians. So they were classifying Hamiltonians, kind of extending this kind of spherical top classification for more general, what are they called? Jacobi transformations or something like that. They did not use, they could have just as well done this, but they did not use did not focus on defining actual configuration spaces. It was more for Hamiltonians. Yes.
Thank you. Have 5 more minutes.
Good. Yeah. So this is not a bad place here. So this is really a toy model, but it's a toy model that manifests basically the key parts of the story in 3D without getting super complicated. So this toy model is diatomic molecules, but if you now look at 2D molecules with more atoms, you see even there you start to see, even still to 2D, you see a richer story. So in this asymmetric case, the symmetry group is C1 or Z1. In the symmetric case that we studied, the symmetry group is Z2. And there you get this minus sign if you do this orthos thing. So these, as I mentioned, are classified by these kinds of fiber things where you have something happening, it's a little pseudospin at each orientation. That pseudospin transforms as some irreducible representation. So the compact notation that people use for this, which are called induced representations, is this irrep up arrow SO2. So this notation tells you the first letter is which irrep the spin acts as, and then up arrow means that there's an action of passive transformations on the space, all of them, so all of SO2. And this notation omits which symmetry group you're using. So it's a little bit coarse, but I put the symmetry group here to make it clear. So like this first line and the second line. They're distinguished by the fact that the symmetry group is different, but the EREP is the same. So anything that's induced by the trivial EREP is basically a classical object, as you can see. Hydrochloric acid is a pencil. Disulfur is a dumbbell. Parahydrogen is also a dumbbell, basically, with a dangling singlet. But then anything induced with a non-trivial EREP, like this B case, like orthohydrogen, is a very much an intrinsically non-classical object, something that is not relatable to a classical object, that has states not able to be occupied by a classical object. And this is this third class that has these topological Berry phases. So that covers C2, but if you go to C3, you see the same story. Now you have SO3 molecule, sulfur trioxide molecule, okay? Oxygen here is red. Oxygen is spinless, so it's the same as a fidget spinner. Okay, you spin it around, it's invariant. And the induced EREP again is A, because it's a classical object. Now, if you introduce spins, you have boron trifluoride. Fluorine is green, and it has nuclear spin. Then you can have these non-trivial EREPs of Z3, which will be cube roots of unity. And so when you do that, you don't get a minus sign, you get a cube root of unity. And this is already kind of interesting because this goes beyond your Bose-Fermi spin statistics that only manifest as plus and minus 1. So even in 2D, as long as you have 3 or more atoms in your molecule, 3 of which are identical, passive transformations actually give you topological Berry phases that are similar to braiding abelian anions. You know, non-bosons, non-fermions. I'm not saying molecules are anions, but what I want to say is that the math used to derive these state spaces and the corresponding monodromy is exactly the same as the math that can be used to derive anionic braiding. Namely, this idea of induced representations with these little fibers giving you these monodromies is the same story can be said about anions, abelian anions. So I guess to continue along the question and conclude, the take home is that the same thing happens in 3D as well. In 3D, you again have 3 classes, no rigid body symmetry. And these are all examples of that. This is a fullerene molecule with 1 isotope in it. This is hydrogen deuterium oxide, so it's deuterated water, so it's not symmetric. This guy is not symmetric under a proper rotation, and that's all we're doing for now. So these are just all asymmetric molecules by this definition. Then there's these symmetric molecules. These have some correspondence to classical objects. They correspond to induced representations that are trivial. The fiber is trivial, but there is some symmetry. The first class corresponds to no symmetry whatsoever and in trivial fiber. So you can really kind of merge them together, but I split them apart. And then the really cool and exotic class, which gives you these monodromies, is the parotational class, where you have symmetries and identical spinful nuclei permuted by the symmetries. And so here you actually have a lot of very common molecules like the ones I mentioned, like water, methane, hydrogen, etc. And here is where you get the possibility of having non-trivial species which have these kinds of transformation behaviors. And in the next session, I'll talk about how the fact that SO3 is non-abelian will mean that the monodromy you will get will not be a scalar, but it'll be a matrix. So while the scalar gives you something that's related to braiding abelian anions, the matrix-valued monodromy acting on your fiber gives you something that's kind of the same math, that's exactly the same math as non-abelian anions. So I thought that was kind of cool. I was very excited about this. So that's basically the take-home message. I guess it's a good time maybe to stop, and thank you for your attention and take questions.
Thank you. Are there any questions?
Hello, thanks for a nice talk. Your study is basically kinematical. but it seems there's a connection to dynamical problem. For instance, when you have a Hamiltonian of coupling two spins, something like SZ1 plus gamma constant S1 point S2, then for special values of gamma, I think gamma is or 1 or 1/2, then you have a monodromy problem in the space of eigenstates. And this is the case where the invariant torus shrinks to the pinch, they have a pinch Tor. So it sounds kind of similar. Could you comment on this?
Yes, yes. Yes, it does sound similar. So there's a whole history of Aharonov-Bohm type effects in molecules. And it happens in a different corner of the state space. So the difference here is that we're dealing with rotational and nuclear spin. The Aharonov-Bohm conical intersection story that I'm familiar with happens when you look at an eigenstate of the Hamiltonian parameterized by nuclear coordinates and move that around in the state space. Sorry, I can't hear.
So when you move in the space of eigenstates of such a bipartite Hamiltonian, you have this monodromy problem. You cannot return. So it has a defect. So
yes,
this monodromy precisely, I think it is very close.
Well, there, the conical intersection monodromy is -1. That's the most you're going to get from this kind of crossing of.
Oh, again, this is kind of when you couple to the spin 1/2 and consider the spin 1/2 as a classical. Something like this?
Well, I guess maybe I'm not sure if you're talking about the thing that I was thinking you were talking about, but the Born-Oppenheimer approximation and the Aharonov-Bohm kind of the Berry phase that comes from that, like Mead Trular.
No. I'm not talking about Berry phase. I'm talking just about you not vary parameters. You just have a space of eigenstates of a bipartite Hamiltonian, a specific, which has additional SO2 symmetry. So in this case, I just read, you have a monodromy problem in the space of eigenstates of such a bipartite Hamiltonian. So in particular, when you go to the classical image of such Hamiltonian, you have a pinch Tor for special values of parameter.
Oh, yes. I think there was also a lot of papers about monodromy and Hamiltonians that were not the Born-Oppenheimer Berry phase. Are you one of the authors of these papers, actually? But yeah, in that case, I honestly can't say I did a full investigation, but I think I will probably say what you already know is that we're dealing with a different state space. We're dealing with position states, and they're dealing with eigenstates. Now, whether or not there's a correspondence, whether or not the eigenstate monodromy is actually coming from the position state monodromy, that could be the case if the Hamiltonian is like diagonal in the momentum basis or in the so it could all be the same monodromy. Why? Because here I can only think of this as this kind of like a true topological Berry phase when I look at position. And if I initialize in any other wave function, I can't really think of it in good conscience as something that's traveling around a parameter space. However, in this specific example, it's so simple that the momentum states themselves are either even or odd, so they actually also have this kind of monodromy, right? They have a sign that like is clearly going to be spit out if you act on them with a symmetry. So in this case, it's so simple that you basically have both of them as even or odd. And if the Hamiltonian is diagonal in J, okay, then you can classify its eigenstates by a symmetry action. And in that case, it could be something related to this monodromy of Hamiltonians.
Okay, Victor, thank you. I think we can continue the discussion perhaps in tomorrow's session. So now, well, we thank our speaker. And we pass to the next talk. The talk is by Frederick Holbeck. It's titled The Geometry of Quantum Contextuality.